So let's continue our discussion on modular invariance of the word sheet partition function. So as we discussed before, if you wanted to compute vacuum energy of these theories, there'll be similar formulas if you want to compute one loop scattering energies. The vacuum energy, just because it's space-time supersymmetry, will turn out to be zero. And because of space-time supersymmetry, you can make a lot of mistakes and still get zero. But that won't be true of scattering amplitudes. So just the consistency of scattering amplitudes in one loop requires all of the structure. It's just that it's easier to discuss it in the case that we don't have to talk about birthdays or things. You could have the discussion of scattering amplitudes in the same way. So we're talking about it in the context of the vacuum energy diagram. Okay. Now, so we had talked about how we multiply this by the x CFTs. So let's say a single free goes on to the power 10, a function of tau and tau bar, and the tau bar is explicit, times some bracket. And this bracket was the fermion partition function, which we argued should be half of minus of minus plus. Let's say to be 8 to be 8 is correct. Because, well, this should also be to be 8. Because there are 8 transverse fluctuations, the coasts cancel the other stuff. And then minus of plus minus plus minus plus plus. And then for the type 2 theories, this is mod squared. Right, you have one of the left movers and similar factor for the right mover. Now, of course, it's really only mod squared for type 2B theory, where you impose the same chirality projection, the Ramon sector, both sectors. Otherwise, it's one of these times another one of that tau bar with plus here and minus there. Okay, so now this is what we got from sort of we try to make a construction of a consistent fermionic theory. Okay, and we got this as a possibility. But to be sure that it is correct, we have to be able to we have to show that it's modular, that this partition function, this fermion partition function is modular. This part is modular then, and this part is modular then, so this part should be shown. Okay. Now, so in this lecture we're going to have a long but important discussion on partition functions of fermionic theories. Okay, before we get to that, somebody remind me of the origin of all these signs. Firstly, why is this a plus? Well, why shouldn't it be with it? Why should it? Why is this a plus, this a minus, this a minus, and this? Right. Tell me about all the signs. Okay, so let's see. So first thing, what is Hamiltonian interpretation of this term? Okay, so I'm going to write trace q to the power h. Everything is of the form q to the power h. This could contain some other insertion and could be in the Ramon or the NS. Okay, the only insertion that we've been talking about is minus 1 to the power h. This could or could not be. So that's what these various four terms are. Let me give you the Hamiltonian interpretation of each of them. Without sign. Just this box is what? Is it traced in the NS sector or the Ramon sector?
It's the NS sector.
Well, how do you know? That's correct. How do you know?
Because you have
I think of this as trace and this is time.
okay, that time. So for time, you're getting a minus sign, so it's actually your
In time. What is the NS sector?
and in space also minus 1.
So which one tells you it's the NS?
It's the space.
Space. Fermions are antiperiodic in space are the NS.
Yeah. Because they are fermions, therefore you have antiperiodicity line and
Good.
they are antiperiodicity in space inside.
Good. So each of these terms has a certain phrase. Yeah. So first you tell me NS or Ramon? This one.
Yes.
This one?
Yes.
NS. This one? Ramon. This one? Excellent. So the handwriting we referring from this is this. Okay, good. Now, what should I put in here? There's a Q to the H. Should I have another insertion? No. Good. Why not?
Because fermions are constantly cases.
Right. The trace of a fermion is the fermionic trace is represented by passing technical percentage. Did we talk about this in the class? Right? It's such a simple two-line demonstration. It's very important. Okay. What about this guy?
You have a minus 1.
Excellent. -1 to the power f times q to the h. Okay. What about this guy?
You don't have it.
With no -1 to the power f, and this one has -1 to the power f times q. For the same reason. Okay. So, okay, I'm going to rewrite this without the q to the h's. That's always there implicit. Without the trace also, that's always there implicit. So just this is 1 in the NS sector, and this is -1 to the power f in the NS sector. This is 1 in the Ramon sector, and this is -1 to the power f in the Ramon sector. Remember we had this with halves. Okay, now let's look at the NS sector. So that's half of 1 plus -1, 1 minus -1 to the power f in the NS sector. What is the interpretation of that? What is this?
This is the projector onto -1 to the power f equal to -1.
It's the projector on -1 to the power f equals -1. Okay.
Or
What?
it's a projector onto the
Odd number, odd fermion number. Right. Okay. So why is this the right thing? So firstly, this is plus. It's telling you that you're counting states with positive sign. Now the relative sign is minus is telling you that you're projecting on a star states with -1 power f is equal to negative. Why is that the right thing to do? Wasn't it true that our JS of projection was -1 to the power f is equal to +1?
because the NS sector vacuum is so
Exactly. The NS sector vacuum itself has -1 to the power f is equal to -1, and you don't see this directly in the. If that origin of the -1 was in the fermions itself, that would be taken into account. But it's not, it's in the ghost state. So ghosts cancel two transverse fermions up to this this factor of -1. Okay? So this is the legacy of the ghosts. That's this -1. Okay. Now let's write this also in Hamiltonian language. That's minus let's say the Ramon sector. Now, whether it's plus or minus tells us that whether we're projecting on a plus or minus one. In the Ramon sector, we've seen that both projections are possible. So that's fine. Why is this minus? We discussed it last class. Somebody say. Yes, because we're dealing with in one sheet of space. Space-time fermions. Excellent. Right. Whether you're dealing with space-time fermion or not, that is whether your state is a space-time fermion or not, depends on how many Ramon sectors you have. Odd number of Ramon sectors is spinner. Okay? So the field in space-time better be a fermion. Better be an anti-commuting. If the spin statistics theorem is to be obeyed, okay, the better be that odd number of Ramon sectors is good. It's an anti-commuting field in space-time. Therefore, has its -1 and +2 space-time diagrams. Whereas even number of Ramon sectors But if you just didn't, it should have no. Right? So if every time you have a Ramon sector appear, if you get a minus sign, that will be the jump. Right? So these minus signs from the point of view of space from space-time is a manifestation of the spin statistics. That deals with how your feature spins contribute in one loop diagrams with a minus sign, so anti-indicators. Okay? So from physics, this is what we expect. But, from the point of view of the worldsheet, that's the question of whether this thing is modular and invariant or not. As we will see, whether this guy is modular and invariant or this guy of the class is not. Okay? So, there's something very interesting here. Just modular and invariant of the worldsheet enforces the space-time spin statistics direction. At least in this context. This is the kind of thing that happens again and again and again in constitutional theory. That things that are necessary from the space-time point of view are enforced by worldsheet, by seemingly different technicalities of the worldsheet. We've seen this previously. We've seen that, a theory with a spin 1 massless boson, or a spin 2 massless field, at least in the traditional way of thinking of these theories, is inconsistent unless you have a gradient. Space-time unitarity ensures that. Okay? So, how does that come about? It comes about precisely that there are these null states associated with these massless fields. These null states are some structure in space-time. Okay? That's out of the worldsheet. So that translate to the space-time gauge invariance. Okay. So, some other structure of the worldsheet gives you space-time consistency. This is another example of that. We'll see this again and again. We'll see it again when we finally discuss worldsheet normalization. Just the vanishing of beta functions. The worldsheet will give you Einstein's equation of space-time. There are many nice, intricate and beautiful connections between space-time physics and worldsheet physics. And this is an example. Okay, so all that was just an answer. Now we want to go and check. We actually want to study the modular invariance of this object. So let's try to do this. So what we started doing last class was to look at a fermion. I said psi of sigma plus 2 pi is equal to minus psi of sigma times e to pi. Okay, so we've got a fermion on a circle which is antiperiodic times the phase alpha. So alpha equals 0 is the NS sector, alpha equals 1 is the non sector, and alpha between 0 and 1 is in, is where I phi alpha. And in everything we've been doing, for definiteness, we will let alpha lie between minus 1 and 1. We'll be choosing a fundamental domain in phases. We don't get any new information. Okay. Now, we want to write out a fermionic Lagrange. The Lagrangian has to be single valued as you go around the circle. So let's look at the partner of this psi Lagrangians. Let's call it psi bar. The psi bar is like the partner under Bose-Einstein. Okay? Both psi and psi bar are left moving. Nothing in what I'm doing is right moving. It's just the Lagrangian is going to be written as psi del bar psi bar plus psi bar del bar psi. Okay? So the Lagrangian is like BC Lagrangian. Okay, so the Lagrangian is psi bar, psi del bar psi bar. Okay, with appropriate factors. Okay? So in order that psi bar, so this Lagrangian is single valued, this phase has to cancel at least quadratically. Okay, so we impose the condition psi bar on sigma plus 2 pi is equal to minus psi bar sigma e to the power minus psi. So the next phase cancels in taking the product. Is this clear? Once again, special values minus 0 or 1 give you ns or 1 boundary conditions, but generic values give you anything. So now we're going to study fermions with these boundary conditions. By the way, these boundary conditions clearly break Lorentz invariance for non-zero alpha, non-zero, non-1 alpha, clearly break Lorentz invariance in space-time. Because you take 8 fermions, which were a priori identical, and then group them into pairs of 2, psi and psi bar, psi and psi bar, psi and psi bar, psi and psi bar, and treat psi and psi bar differently. Okay? So what this will do is to preserve an probably an SU, probably like a U4 out of exponents. One in which you rotate the psi's all themselves under unitary transformation and psi bars under U dagger. Okay, so this would be like Lagrangian is psi L bar psi bar. Okay, there are 4 of these guys. Let's call that A and A. If I rotate psi by a unitary transformation and psi bar by the anti-unitary transformation, this Lagrangian is preserved. Boundary conditions are also preserved by this rotation because all psi's have the same boundary conditions. And all psi bars have the same boundary conditions. We're not allowed to mix psi's and psi bars because psi's and psi bars have different boundary conditions. Okay? So it breaks the Lorentz invariance SO8 of space-time into a U4. Okay? So these are this is true for every alpha except 0 or 1, where the component leaves actually have the same boundary condition, but psi and psi bars have the same boundary condition. So there's a large application. Okay? This is why we will not, for studying Lorentz invariant spacetimes, be interested in any value of alpha except 0. But later on, when we start studying compactivity and string theory, start looking at theories that break full 10-dimensional Lorentz invariants, such kinds of theories can and will be interesting. That's why we're studying them here. Okay? Fine. So let's go. So let's try to understand the mode expansion of psi and psi bar. There are 4 psi bars. Not going to write the indices. They are the same. So psi, how does psi mode expand? Psi is equal to. Now look. Let's write this phase as e to the power I alpha minus 1 by into pi. Okay, so I absorb the minus 1 into e to the power minus I pi. Okay? So, how does this go? Psi of sigma is expanded as sum over n e to the power I n sigma plus I n plus alpha minus 1 by 2 sigma. Okay? So that the sigma goes to sigma plus 2 pi, this part goes to nothing, with this part which is the phase that you want. And similarly, psi bar will be expanded. Sigma will be expanded as sum over n e to the power I pi into. Now, I want to write a phase that correctly captures what we have, and I want to write it so that it's positive. Let me write it so that that's not satisfied by this, but this will be so. Sorry, I can. It doesn't make a difference if I write plus 1 minus 1. Minus 1 is equal to pi, pi is equal to sine pi. And I can write the same here, so plus 1 minus alpha by 2. Okay? What? Why this choice? Because I want to write in convention such that n 0 and greater are annihilation. And n, I want positive n to be positive frequency. So that. Okay? So, you say, as we just discussed, if n is 0 or greater, this is a positive number in both cases because of our choice of range alpha. Okay? So now if we try to write down, let's try to write down what the 0 point energy of this guy is. Okay? So the 0 point energy is minus half, because we're dealing with formulas, times sum over n is equal to 0 to infinity of n plus 1 plus alpha by 2 plus sum n equals 0 to infinity n plus 1 minus alpha by 2.
You also modes multiplying the exponential.
Yeah, we have that. Fine. Maybe I call these sine A plus this phase. That may be better notation. Okay? Now let's evaluate each of these sums. Let's remember how we've done this about 20,000 times. Let's do 20,001 time. Okay? Stepping in minus 1. You remember, I'll just remind you of the pieces. Such sums always give you minus 1 by 12. That's from the Euler-Maclaurin formula. So the Euler-Maclaurin formula works when you have half of x0. Here we have all of x0. So we should take half of x0 out. So we have half of 1 plus alpha by 2. And then similarly here. Okay, so let me write this as minus 2 by 12. There's one factor from each of these terms. Then half of 1 plus alpha by 2 plus 1 minus alpha by 2. That accounts for the fact that we needed to take these pieces out before applying the Euler-Maclaurin formula. And then the final term was that this gets converted into an integral over x, but from this to the cutoff, rather than from 0 to the cutoff. Okay? So we have to subtract the integral over x from 0 to this value in order to get to be subtracting a universal cutoff value. Boundary condition independent piece. So we should that value as well. It's minus 1 plus alpha the whole thing squared by 8, because this thing squared by 2. And then minus 1 minus alpha the whole thing squared. So this is 0-point energy of the system. Let's try to evaluate that. So this is minus half into minus 1 by 6. Now the alphas cancel here. Halves add up to give us a 1, so plus half. And here the term that's linear alpha cancels. So the term that's 1 gives us minus 1 by 4 minus alpha squared. Okay? So half minus 1 by 6 minus 1 by 4 is 1 by 2. Because that's 6 minus 2 minus 3 by 2. So 1 by 12. So that's equal to minus half into 1 by 12, 1 minus 3 alpha squared. So 0-point energy is what that is. So 0-point energy is worked out to minus 1 by 24 into 1 minus 3. Is this clear? Okay, let's do some consistency checks. If we said alpha equals 0, we should get 0-point energy of the NS vector. But that's minus 1 by 24, that's good. Because that's the right answer to formula. Okay, and if we did alpha equals 1, we should get the answer that will cancel the Ramon sector. That's we get 0-point energy in the Ramon sector. That is the 0-point energy that cancels the 0-point energy of Godot. So it should be plus 1 by 12. So that's what we get. So it's right. Okay? Now we can check this from another point of view that will prove useful for various things. Okay. The other point of view that I'm going to use is to try to understand this answer through post transition. Okay? So what I'm going to do is take these fermions that are antiperiodic in distraction, I mean that following this periodicity, and try to understand what the equivalent boson is. Okay? So let's see what this psi. Let me write down an expression for psi. Psi n is equal to integral psi of z divided sometimes z power minus half, and then whatever will cancel this number. Right? If we write psi as sum over m psi m by z to the power half plus m, where m is what appears in this space. Okay? So we should write plus n plus this space. Right? So in terms of conjugate textbooks, that's the formula appropriate one over 2 pi I. Right. And similarly, psi bar n is equal to integral psi bar z bar minus half plus n plus 1 minus alpha. Okay. Now, psi n and psi bar n for positive and zero number, for n greater than or equal to 0, annihilate the vacuum. Right? So, suppose the operator due to the vacuum is O vacuum. What OP do we want? We want that when n is equal to 0, the power of z is completely cancelled. So, we want that psi with OB okay, and we can actually simplify this power of z. That's equal to, this power of z is the 1's cancelled here. So it's z to the power n plus alpha. And this is z to the power n minus alpha. So if we set n equals 0, we want psi over OB to cancel this. So that should be equal to z to the power minus alpha. Whereas psi over OB should be z to the power alpha into psi bar over OB. Should be z to the power. Is this clear? Everyone looking at the puzzle? Let's slow down and you tell me what the puzzle is. Let's plug this in. Suppose this works. Then what will you get? This minus alpha by 2 would cancel the alpha by 2. So, for n greater than or equal to 0, we would just have a factor of z to the n times psi. And so this would be analytic. So we can see. So you see that with these OPs, psi n and psi bar n both annihilate the vacuum for n greater than or equal to 0. Which is what we do. Is this clear? Because n greater than or equal to 0 are annihilation operators, n less than 0 is creation. Exactly. Yeah, okay. Well, there's something special that happens when alpha is exactly equal to 1. Let's see. something.
Sorry, actually, what is the operator? I mean, what is the operator that we're taking to the vacuum here? Or?
The vacuum is defined by psi n on v is equal to 0 for all n greater than 0, psi bar n on v equal to 0 for all n.
Now, in the operator language,
In the operator language, it must be. Right? So the operator given to the vacuum is OV. And we just check that it satisfies these and right. It's the right thing, right? I mean, everyone agrees? Okay. So now we can solve for this. We know psi is equal to pi h. It's clear that the answer is going to be e to the power I zeta h. OV will be, it's clear that OV will be pi zeta h. Okay? So if it was e to the power I zeta h, then psi on OV would be the minus sign from the i's and the minus sign from the z. So it would be z to the power zeta. So if we look, so I'm saying the psi of z times e to the power I zeta h of 0 is equal to z to the power zeta times that. Okay? But we want z to the power minus alpha by 2, we choose zeta to be minus alpha by 2. So our choice is okay. Little suspicious of this minus sign. That's what we got. I may have made a calculation with an error with minus sign. You will see it. Anyway, let's go ahead. Let's go ahead. Let's get the final answer and we check these questions. Okay. Fine. So we've got the operator given to this to the vacuum. Now we wanted to check this answer against this. Okay. So what is the dimension of this operator? Delta is what? Tell me. Alpha squared by excellent. So what should the ground state energy of this? What should the ground state energy? Alpha squared by 8 plus or minus C by 24. C is what? C is 1. Each fermion has central charge half, 2 fermions have central charge 1. Or a boson has central charge 1. Okay. So this is equal to minus 1 by 24 into 1 minus 3 alpha squared. Matches. Okay? So, now, okay. the partition function of these bosons. But I'm going to do something a little more technical. You see, now that we've bosonized, we have this clear fermion number current operator. An operator that under which psi has charge 1 and psi bar has charge minus 1. It's the current which in bosonic language is ILH. Okay? So let's call that the charge of that current Q. And the figure I'm going to compute is trace of e to the power I q pi times q to the power in a sector labeled by boundary conditions that have an outlet. This is the one table. Q is the usual e to the power I 2 pi I tau. Oh, Q. The capital Q is the charge generated by ILH. It's the shift charge. The charge Q is 1 for psi minus 1 for psi. Okay? Now, and with the beta. With an outlet. So if I set beta to 0, I put no charge. But if I set beta to 1, this becomes minus 1 to the power. Okay? So that's the motivation. I want like I had this extension in alpha, the boundary conditions, and it allowed me to interpolate between Ramond and NS. I want some interpolation between the straight partition function and partition function to the minus 1 to the power. Okay.
So this is partition function.
No, it's funny kind of condition. So let's write it down. So this will be given by path integral. So this is 2 pi, this is 2 pi tau. With the boundary condition that psi of sigma plus 2 pi, as before is equal to minus psi of sigma pi of right? And psi of sigma plus 2 pi tau is equal to minus sigma psi of sigma into e to the power I pi b. Similarly, psi bar had alpha goes to minus alpha. Psi bar is beta goes to minus beta because beta has charge minus 1. Because psi bar has charge minus 1 q. While psi has charge 1. Okay? So psi bar has the complex conjugate combinations. Okay? So now I'm going to write it. Is this clear?
First one is for signal, the second one is for tower.
Is this axis. Thank you. In the complex plane. Z. Okay? Now when we evaluate this path integral, try evaluating it as a trace, the way we usually do. Okay? And then we're going to discuss its modular transformation properties. So first, let's evaluate. Fine. So, first thing we're going to do is to deal with the ground state energy and ground state charge. So ground state energy we already know. So we get a q to the power minus 1 by 24 into 1 minus 3 of this for the ground state energy. But we also in French language have this factor. So this factor gives us an e to the power. So what is Q? What is the charge of the vacuum? Yeah, minus alpha. Minus I pi alpha beta from the vacuum. And then all that remains is what we get from the oscillators. Okay? So then we have product domain. 1 plus q to the power n plus alpha plus 1 by 2 into e to the power I pi beta into 1 minus 1 plus q to the power n plus alpha minus 1 by 2 into e to the power minus I. Okay? So this is our answer. This is our answer for this. Well, 1 minus. Right. Obviously positive. N is equal to 0 to infinity. And that's a full partition. Now this partition function can be rewritten in terms of some fancy theta functions. As always in this game. And the way people normally proceed after this point is to rewrite this in terms of theta functions and use known mathematical properties of the modular transformation property, modular transformation properties of theta. However, that's not very satisfying unless you already know the transformation properties of theta functions. So I'm going to try to argue, I'm going to try to help you understand the modular transformation properties as far as we can from physics. Because it's good to have a mathematician to verify them. But we'll try to do it as physically as possible. Okay? So, we're not going to use this formula. This would be one rule. Write out this formula, evaluate in terms of theta functions, and then look up a mathematics book. Or try to think in terms of this formula. Understand modular transformation properties, and that's a good route. But that's not the one we're doing. I evaluate it just so that we know that it's not something abstract. It exists. So we don't even really need that formula for anything. Except for actual evaluations. Okay. And so what are we going to do? We want to understand the modular transformation properties of this object. So let's call this object, let's give it a name. I'll call it Z alpha as a function of that. Okay? Now, this Z alpha beta is what? In a way, it's a partition function with these boundary conditions. So, now what I'm going to do is to first make some naive arguments. And then see how far these naive arguments are correct. So suppose there really was, some proper, well-regulated diffeomorphic invariant path integral that computed the Z alpha beta. Then what could we say about Z alpha beta of tau plus 1? You see, so what do we have? We've got when we go along this cycle, our boundary condition picks up a phase e to the power I pi. We pick up a phase e to the power I pi alpha plus or minus. When we go along this cycle, which is the same as this cycle, we pick up a phase e to the power minus I pi beta times the minus. So what do we get when we go along this cycle? What are the boundary conditions? Field here, connecting field here.
So it should be this plus this.
This plus this. So what should tell you exactly? With the alpha plus beta with a plus sign. Even power I pi alpha plus beta with a plus sign. Or if we want to write it in this language, it's alpha plus beta minus 1 with a minus sign. So, naively we would guess that this is equal to Z alpha plus beta minus 1 You see, what is the logic? What you want to do is specify some periodicity on the torus. So if you specify this periodicity and these boundary conditions, that's the same thing as specifying this periodicity and these boundary conditions. Okay? This has been emphasized in we'll come back why it's
They think of somehow taking that triangle.
what?
They think of somehow taking the upper triangle and putting it on the side.
Just calling this side your new tab.
Yeah, so they, okay. The right hand side is written, the parallelogram with the diagonal as it.
Right. Right.
Somehow we are taking that triangle and saying with that triangle.
You see, what we're doing is specifying an identification of the plane. We've got some set of lines vectors. So whether you say that this and this or this and this, it's the same identification. Because this is equal to this plus this. You specify these two periodicities, you specify the same torus. That's the idea of modular invariance. Now, there are many different cycles of the torus that you have to put two statements of identification.
This is modular invariant.
It's modular invariant, it should be true. Moreover, if you have written down a genuine path integral on the torus of some well-defined field theory, suppose it was just a genuine path integral, something you could regulate genuinely. Then it would be modular invariant because a path integral is a path integral on the torus, not on your parameterization. Okay, so were it an honest path integral that you could regulate in an honest way, then this would not be a condition you have to impose, it would be true. Okay? So it's that a question of whether it's a genuine, honest path integral that we have to come back to. Okay, but let's figure out the other transformation properties. Okay, the other transformation property is the tau goes to minus 1 by tau. The tau goes to minus 1 by tau. Okay, so how do we do that? Look, suppose we've got a W coordinate that's such that W is equal to W plus 2 pi and W is equal to W plus 2 pi tau. Okay? So in particular, it's also true that W is equal to W minus 2 pi tau. Okay? Now let's look at W prime, which is equal to W by tau. To make the second transformation, we go to this new W prime coordinate. And new periodicities in terms of W prime are W prime is equal to, sorry, this I wanted to leave this, but this I want to say is equal to W minus 2. W prime minus 2 pi tau. And W prime is equal to W prime plus 2 pi. Now I choose, this is my fundamental identification rather than this, because by convention we choose tau to have positive imaginary. The identification vector have in the upper part, right? A positive imaginary part. Then 1 by tau would have negative imaginary part. But minus 1 by tau would have positive. So I'm just choosing the identification vector here that has positive imaginary. Yeah, that's why I choose this minus side tau. This is the usual reason that this tau is minus 1 by tau and plus 1 by tau. It's true that tau is plus 1 by tau also. I figured by convention we choose tau to be the upper. Okay? So, now let's look at this. We have a conformal field theory, so long as the path integral respects conformal scale invariance. Whether we go to W or W prime, it should make a difference. Okay? we get the phase that we have along this axis. Okay? So, now, this axis is our space direction, so whatever phase we get, we should write that here. But what phase we got here was beta, so we should write beta here. Right. And along this axis, we get whatever phase we had around here. Now, when we went from omega to omega plus 2 pi, we got a plus I pi alpha. So, when we go to minus 2 pi, we get a minus 2 I pi alpha. Okay, we should write it minus 2. Okay. So these are the two naive relations. These are the two things that we naively. Okay. What? It's not supposed to matter. You see, any modular, anything that can be defined by a genuine power integral for whatever second charge should have this problem. This is not something that to do with a conformal transformation. It's just saying the path integral is well defined. It is well defined when you specify the boundary conditions like this or like that, it shouldn't matter. Okay, now before thinking a little more deeply, about whether this is true or not, let's test the experiment. Okay? So, let's say that we calculate the Z alpha beta the way we did, by calculating it as a trace. Now, let's evaluate what happens when we take tau to tau plus 1. So, when we take tau to tau plus 1, what do we get? You see, tau to tau plus 1 just shifts what Hamiltonian interpretation we get for tau plus 1 compared to tau. We've seen this before when we were discussing the bosonic string, that the real part of tau is the chemical potential that couples to L0 minus L0. Is this right? We had e to the power 2 pi r. That's right. Let's remind ourselves of it. We have q to the power 2 pi I tau times q bar to the power 2 pi I tau bar. Well, and e to the power, like q to the power, sorry, okay. Q to the power L0, q bar to the power L0 bar, and q was equal to e to the power 2 pi I tau, q bar was equal to e to the power minus 2 pi I tau bar. Okay, so let's write this as e to the power 2 pi I times real tau plus I in tau, and this is times L0, and this is 2 pi I L0 bar, the minus sign, real tau minus I in tau. So let's look at what happens to real tau. So real tau, we have e to the power real tau times 2 pi I into L0 minus L0. Next is chemical potential for L0 minus L0 tau. Okay, so if you shift real tau to real tau plus 1, the contribution of every state shifts by L0 minus L0 times e to the power 2 pi I. Okay? So, if you evaluate it like a trace, each state, the contribution of any state of a state S goes to e to the power 2 pi I L0S minus L0R. So, this modular invariance business, okay, this modular invariance business, let's say we look at the simplest case, suppose alpha and beta were just 1 or 0, anything simple. Okay? This modular invariance business is tied to the assumption that L0 minus the spectrum of L0 minus L0 bar is integers. See, modular invariance of this sort under tau is tau plus 1. This naive statement of modular invariance will work if and only if the spectrum of L0 minus L0 bar is integers. Now in our theory, we're looking at a theory of just an analytic formula. So there's no L0 bar. So it's just a question of whether the spectrum of L0 is integers. But what is the answer? The answer is that it's not integers. The oscillator has integers. Suppose alpha was 0. This is the case for which we have the argument. The oscillators give us integers. Okay? But the 0 point energy does not. One second.
We have a 2 to the power some fractional power, which gives up a branch cut when you root out going forwards.
Right. No, it's not. Yeah. The point here is the 0 point energy.
Yes, so that the fraction.
The thing in the 0 point energy. Exactly. Okay? Right.
Because when tau plus 1 q goes to q e to the power I/5.
Right.
Which shouldn't matter if you have a good function of q, but you have a q to the power something. So when
exactly.
you rotate q once, you cross a branch because you have a fraction of say.
Yeah. It's right. Let's work it out to start with. Just the simplest case of alpha equals beta equals 0. So we're in the NS sector. Okay? Then the states all have integer energies modular the contribution of the 0 point energy, which gives us minus 1 by 2. Okay? So every state under tau goes to tau plus 1 picks up the same phase. And the contribution of that phase is entirely from the 0 point energy. It's e to the power I L0 of 0 point energy times this business. That's 2 pi. Okay? So, now, you see, this motivates actually the correct task. Which, let me write it down. The correct version of this is Z alpha beta is actually equal to, it was 0 point energy, so that is yeah, and we have to check which way it goes. It's the minus the 0 point energy because the tau plus 1 has the phase that comes from 0 point energy. So I'm writing it as Z alpha beta of tau is equal to something times Z of tau plus 1. So I should get the reverse sign. So e to the power plus 24, 1 minus 3 alpha squared into 2 pi. Yes, 2 cancels to 12 pi. Right. Times Z alpha plus beta minus 1 plus what? It's a statement of violation, modular invariance for the path integral of the single line.
why doesn't
Okay. Now, I haven't completely justified it because we haven't completely worked out the argument in the alpha beta sectors, in a sense. Okay. But I'm going to ask you basically to look at the argument that I've given you and try to convince yourself that this is true. I think let me just check the slide.
it's plus 5
This the sign is opposite of this? Let me check. Kurchinski is the same sign. Sorry, you were telling me what you thought it was opposite sign? I've reversed the 0 point energy because I should have written it with 0 point energy on this. Z of tau plus n plus 1 will pick up the contribution of 0 point energy times Z of tau.
energy
Had a minus sign and I reversed it.
Oh, you don't have a minus.
I don't know. Plus plus. Okay, good.
So if that modular invariance at a special level of alpha is 1 by
Right, we get back up at alpha equals square root 3. But we will be interested in the superstring in alpha equals 0 and alpha equals 1. So that we don't have that freedom. Okay, so we'll have to do something different.
Is there any free from this formula also? Because this gives me that factor and the treatment with the here the shift cancels.
Yeah, shift cancels out to the extent that it should. Because you're supposed to get this replaced by alpha plus beta minus 1. That's right. So you should be able to, yes, you can relatively directly see it. You write this formula, just check in some term like a way that this is true. You can quite easily see it. Okay, good. Yeah, so that's what that's one way of completely convincing yourself that this is the right answer. Okay, now let's go back for a minute and ask what was going on. How could it be that we're doing the same path integral? How could it be that we get different answers and it just doesn't make sense? It sounds like it's not making sense. And the point is, as usual, that what's going on here is that the path integral is hard to define. You see, suppose you got a theory. Let's talk about this. You see, I've talked about this with fermions, but it's actually the same for boson, the bosonic representations. So let's talk about it in bosonic language. What's going on? We've got this bosonic path integral. Now, why are we getting a unique answer on the torus? And the point is we don't really have bosonic path integral because all that we have is the left moving centers for bosons and not the right moving centers. Had we had both the left movers and the right movers, then we would have 0 point energy from it. Left movers, 0 point energy. The right movers would cancel. Okay? Now, when you have the left movers and the right movers, it's a genuine boson. It's an action that can be discretized in the torus. Right? So you can replace it by a lattice action, evaluate it on a computer, and you must get the same answer. This thing as well, if I continue to limit which we know it does. You must get the same answer no matter how you factorize the torus. Similarly, in fermionic language, if you had both the left moving fermion and the right moving fermion, then you've got some genuine action fermions, which you can take and regularize somehow by Pauli-Villars regularization. In some diffeomorphic invariant way. And you get the same answer no matter how you parameterize the torus. But in this situation, in a situation where you are only left movers, that's a path integral. That's a very abstract object. Okay? It's not something you can discretize and put in a computer, or even basically regulate in a large diffeomorphically embedded way. So that's the problem. Okay? These large diffeomorphic embedded.
There's a problem even in small diffeomorphisms.
There is a problem. You see, with small diffeomorphisms, there would have been. Right, there is a problem actually.
Just
C minus because C minus C bar is. But suppose I could have taken. Yes, there is a problem even with small. At this level, there is a problem even with small. You can manufacture examples where you would have no problem with small diffeomorphisms, the problem with large diffeomorphisms, just by choosing one left moving sector with one boundary condition and right moving sector with another boundary condition. You can arrange C to be equal to C bar, but just because boundary conditions are different, the vacuum energies will be different, and you'll have a problem with the large diffeomorphisms, though not the small. Though in exactly this example, you would even have a problem with it. Okay? Fine. Now, but that already brings out the problem. So clearly, we're dealing with left moving sector, no right moving sector. Diffeomorphisms are anomalous, and so it's no surprise that this large diffeomorphism it doesn't work as you would expect. As we said, if you had left movers and compatible right movers, then it's sort of clear you could do everything properly. Discretize the torus, put it on the computer, doesn't matter how you parameterize the system. Okay? And if you had now the left moving path integral is some function of tau. If you added in right movers with exactly the same compatible boundary conditions, you get the corresponding complex conjugate function of tau. Okay? So, in order to define this path integral, in order to define your path integral, one way of defining it is, add in the right movers, compute the path integral, that's totally right? It's some function of tau times some function of tau bar. Okay? And extract out that function of tau, roughly take the square root of that. But there's an ambiguity in that. The ambiguity is the phase. Okay? If I've got mod a squared, let's say that I've got some a of tau and a bar of tau bar. And all I'm given is this product. Okay? Then, because I know that a is a function only of tau, there's not too much ambiguity in how to decompose it into a mod square. There is some ambiguity in the sense that a goes to a tau into e to the power I beta, and a bar goes to a bar tau bar into e to the power minus I beta. Okay, would be as good a decomposition as a of tau and a bar of tau. Of course, since a can only be a function of tau, and a bar will be a function of tau bar, beta can't be a function of anything. It's just be a number. Okay? So there's a phase ambiguity in this part. If this is how we try to define our path integrals, it sounds like a reasonable way. There's an ambiguity up to phase, and this ambiguity up to phase is independent of tau. Okay? So these large diffeomorphisms could exploit this ambiguity up to phase independent of tau. Let's go back to see what we found here. We found exactly that. We found a phase that doesn't depend on tau when we do one of these large diffeomorphisms. Okay, so this is what's going on. It's not a surprise, but it may be a problem. It may be a problem because we want the quantity that appears in string theory just to have modular dependence. We don't care why, whether it's left movers, right movers. I mean, we don't care about any of that. In the end, it has to have modular dependence. Now, you might say, well, in string theory, we have both left movers and right movers. So why are we worrying so much about just the left moving component? The point is that we've got a very particular combination of left movers. And it may be no problem if all the guys pick up the same phase. But if we get different relative phases, we're sunk. There's no way that the right movers can cancel it. Okay? And that can, and as we will see, will happen. If general, unless we're careful. So the right mover can cure an overall phase but not different relative phases. Okay, correct. Now, with this understanding of this phenomenon, we can ask what happens when under tau goes to minus 1 by tau. Now, under tau goes to minus 1 by tau, there's a very simple special point, namely tau is equal to r. Because then minus 1 by tau is also equal to r. Okay? So because this point is sort of self-similar, okay? Right, at least if both boundary conditions were the same, right? If we're both Ramon, we're both in Neville-Schwartz, it's obvious that under tau goes to minus 1 by tau, you don't get this. Because under tau goes to minus 1 by tau, at this point, you go back to the same point of the integral. And we calculate that the phase does not depend on tau. Okay? All these arguments are a little fluffy, it should be checked with formulas. And really, there's really, in the end, completely satisfying ways to go back, write out the formulas and check, which is what this theta function is. But anyway, this is at least motivation for the correct result, that this naive result is correct for tau goes to minus 1 by tau. Okay? But gets modified to this guy for tau goes to tau plus 1. Okay? So in order to our worries about moduli invariance should be worries just about tau goes to tau plus 1. Tau goes to minus 1 by tau looks after itself. Okay.
There is a point where.
So let's look at a special case. The special case is alpha equals beta equals 0. Okay? At least at this point.
I understand that because this is
Then, okay, yeah, and more generally, if alpha is equal to beta, it just is obvious. Okay, now, why is it true more generally? Because then the integral is just the same. Tau goes minus 1 by tau, it's the same integral at when tau is equal to 1. So obviously, you get the same answer. Okay, now, you ask, so, I use that as motivation statement always happens. Now, is that argument that will understand? Let me see. So what we could have is a phase that vanishes when alpha is equal to beta. Let me see. What is there? Is there an argument? There's some simple argument we give to that. No, but that's okay. You see, that's okay. You see, because whatever alpha and beta, you do the tau at tau equals r, the part, this thing becomes this part. What am I saying? What am I saying? You see, what am I saying? I'm saying that no, but in terms of traces, right? So let's think of this as, the way we've actually computed our formulas is with trace. So I should be asking the question, if I flip the, certainly in terms of the trace formula, it's not obvious.
Same argument is saying that that phase won't depend on tau.
But it could depend on alpha.
Yeah, but so for a particular value of tau, that phase would be something.
Right. So we've argued that this phase, which is independent of tau, has to vanish when alpha is equal to beta. I think that's clear.
But this is a
Okay, we will alpha sigma.
Okay, alpha equal to beta equal to 0 is of course that
It's certainly true. Yes. Yeah. Yeah.
So at that value of tau, if that phase is 1, and that phase is independent of tau, then it is.
But it could be independent of tau and depending on alpha.
and alpha and beta equal to 0 is 1.
It is one, and you could probably make a more general. Wait, so there's probably an easy, simple generalization. Let me give you an example. Okay, let's not spend it now. I'll try my next class to give you. I'll see if I can come up with a better argument. You know, what we're trying to do is to finesse using theta functions, okay? And maybe in the end we'll. So I'll try to give you a better argument if I can come up. I'll try to think about it through. There should be one. I'll try to think up a better argument for more general argument.
Because tau going to tau plus 1, I think one can just see.
From the formula. It's just state by state. So you won't be able to see tau equals to 1 by tau from the formula because that requires a Poisson summation.
Yes.
Okay? Now of course you can do the Poisson summation. You can do the Poisson summation, but then that's basically what the theta function is. Okay, so that's cheating. That's not using some general arguments to get the answers. It's doing what the theta function. Okay, and certainly if you do that, you get this answer. Okay, but there may be a more. I'll try to think it through. There may be a more, in principle, general way to see this, which I haven't properly enunciated here. Due to at most some motivation that tau goes to 1 by tau is better than. At least there's no obvious problem with tau goes to minus 1 by tau, and some special value is it doesn't become it. That's the extent to which I argued it. It's true that there is no problem. Okay, that's the naive thing. It's true, as you can see by essentially a Poisson solution. Okay. But okay, I'll try and see if I can do better than that. I'm getting to it. Okay, very good. So let's continue on. So now we just take these two relations here. This guy and that modified face. So now let's go back and look at the thing that we were really interested in. So the thing that we were really interested in was, remember, so we had this guy, minus. Now let's work this in terms of all angles. So that's Z 0, 0. Right? And now this is in the path form because we're taking pairs of fermions and paired them up into this length. So 8 fermions is Z0, 0 path. Then we have minus of this guy, which is minus plus. Now this is what? This is Z. We put the spatial conditions here, so that's 0, but this is 1. So minus Z 1, 0 to the 4. Okay. Then we had minus this guy. Plus minus. So that's Z 1, 0 to the power form. And then plus minus Z 1, 1.
You can work with complex. So there will also be tau to minus I.
Yeah, we often choose by dimension the tau. Doesn't matter, you change it. Okay, so this is the combination that we were interested in. Now let's look at this combination. So under tau goes to minus 1 by tau, we've claimed that there's no body because each of these objects is by itself. Okay, so now let's look at what happens after tau goes to tau plus 1. So after tau goes to tau plus 1, what is the phase that you pick up? You see, the phase is determined just by the alpha value. But what you get is is determined by both alpha and beta. So what happens to this guy? This guy goes over to, well, firstly, alpha goes to alpha plus beta minus 1 now. Minus 1 and plus 1 is the same thing. So that goes to Z0. Okay? To the power of 4. And with what phase? With phase e to the power pi I by 2. Okay, let me replace this 4 by, we know the right answer is 4, but suppose it was actually m. So we will have 12m. We know that the actual number of transverse fermions is 2m, is 8. But suppose the actual number of transverse fermions was 2. This doesn't, just to see. Okay, we'll in the end set n. So we get this, then we get minus of this. Now let's see. So 0 goes to 0, but beta goes to alpha plus beta minus 1, so that goes to 0. Okay, and with what value of phase? Once the same value. To the power m, and then e to the power I pi m by 12. Okay, just because we need the same value of alpha. Okay, then we get here, we get 1 goes to 1, but the 0 goes to 1 plus 0 minus. Yeah, that's good. So we get minus Z1 0, right? Because 1 goes to 1 and this goes to 1 plus 0 minus 1, so that's 0. So the value of the phase now is different because it's determined by this alpha value. Alpha was 1. So we get twice the value in opposite side. So minus e to the power minus 2I pi by 12. Alright? And this guy goes to the same phase, e to the power minus 2 pi I by 12m into Z11. That remains constant here, 1 minus 1 plus 1. Okay. So now what do we see? By doing the tau goes to tau plus 1 transformation, this guy goes to this guy goes to this guy, but there's a relative minus sign. Right? Because these two came with minus sign flip. Whereas this guy goes to itself, but with a different phase, and this guy goes to itself with a different phase. Okay. So let's try to absorb away the minus signs. So what do we get? So we get, after the modular transformation, we get the phase for Z00 to the power 4. We get Z00 to the power 4 into e to the power I pi m by 12, and then let's call it plus alpha. Or let's call it minus alpha. Minus alpha. Okay? Plus minus Z01 to the power 4 into e to the power I pi m by 12 minus. Okay? I'm talking of the phase in here. The minus sign. Okay? then minus z10 to the power 4, no minus sign, that means minus I pi m by 6, and plus minus z11 into the I pi m by 6. So the modular transformation takes this guy, which is the sum of these guys with no faces, does the guy which is the sum of these guys with these faces. Okay. Now, as we know, the right movers will give us the opposite faces. What we're worried about is the relative face. Okay, what we're worried about is the relative faces. So the relative faces, what we need is that all of these guys transform to the same face. What the faces doesn't matter, that cancels with the right face. Okay, so what is the condition that imposes? The condition that imposes is that so let's take a factor of, let's write this in terms of multiples of 2 pi. Okay, first let's just check that it satisfies your m is equal. So say m is equal. What phase do we get here? This guy is 1/3 pi minus I pi, so it's minus 2/3 I pi. So minus 2/3 I pi. And this guy is minus 2/3 I pi. Oh, this guy is minus 2/3 I pi. Okay? So for n is equal to 4, all phases are e to the power minus 2 by 3. Okay? But more generally, one could ask the condition, when is I pi m by 12 minus I pi equal to minus I pi m by 6 modulo 2. Right? So that's the condition that I pi m into 1 by 12 plus 1 by 6 is equal to I pi modulo 2 pi. Okay? So that's the condition. So this factor 3 by 12 is 1 by 4. I pi m by 4 is equal to I pi modulo 2 pi. So that works at m equals 4. But then the next time it will work is when m is 8 plus 4. Right? So, yeah, we have one already, minus 9. So m is equal to 4, m is equal to 12, m is equal to 20. So just modular invariance, okay, just modular invariance tells you that the number of transverse dimensions with this GSO projection, the number of transverse directions has to be 8, otherwise it would have to be 8 plus 16, so whatever that is, 24. Because we have very good other reasons for choosing 8, cancelling the central charge. But even just the modular invariance 8 was a special value. You see, had it worked out with central charge only cancelled, but there were 6 transverse dimensions, it would be impossible to make modular invariant partition function, which was GSO projected. Okay? So many things have to come together to give you a consistent answer. And that n equals 4 works because it's part of this consistency issue. The last thing that I wanted to point out about this was that this minus sign was crucial in turning right. Sorry. This whole thing works here. This whole thing works here. Sorry. There's one more thing. This whole thing works here independent of this term. You see, because this term just went to itself. This term just went to itself, and there was a minus sign flipped between these two that was crucial in getting the phases to match. Okay? So this modulate variance argument would not have worked had we imposed the plus projection. Because then you would have got the relative minus sign flip between these two terms to match with the extra phase of this kind. Okay? So this tau goes to tau plus 1 business. Okay? Works only when you impose the correct years of projection. Okay? But it leaves the sign of this term undetermined. However, the tau goes to minus 1 by tau flip couldn't work without this sign. Why is that the case? It's true that tau goes to minus 1 by tau has no anomalous part. But it does have the naive action. And under the naive action, this thing changes. So let's see what happens after tau goes to minus 1 by tau. So tau goes to minus 1 by tau is a fancy way of saying flip the two cycles. Okay, so what happens to minus 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 plus minus minus